Next is buoyancy and Archimedes principle. Buoyancy is the phenomenon of experiencing a force exerted by the fluid when the body is partially or the wholly immersed in the fluid, and the force is called the buoyant force. So we can write buoyancy is phenomena of experiencing a force exerted by fluid when body is partially or wholly immersed in the fluid, and the force experienced by the body is called the buoyant force. Similarly, Archimedes principle states that a body immersed in a fluid experiences an upward buoyant force, and it is equivalent to the weight of the fluid displaced by it. So we can write that Archimedes principle states that when a body immersed in a fluid experiences a force which is upward buoyant force, and it is equivalent to weight of fluid displaced by the body. Suppose in a liquid there is an elementary cylinder which is having the area of cross section say dA, and upper surface is at depth h1 and lower surface is at depth h2. Density of the liquid is rho, therefore the net force acting on the elementary cylinder can be calculated by considering that F1 is acting downward and F2 is acting upward, because F2 will be larger because pressure at the lower surface will be higher because of the more depth. So we can write that elementary force on the cylinder will be F2 minus F1. This will be equal to, this F2 is due to the pressure, so it is P2 at the lower surface into area of cross section dA minus P1 into area of cross section dA. It will be equal to, because pressure is equal to rho GH because of the liquid column. So we can write at lower surface it is density is rho into G and height is H2 into dA minus rho into G into H1 into dA. It can be written as rho G into H2 minus H1 into dA. Here this H2 minus H1 into dA is the elementary volume displaced by the object. Therefore, we can write it is rho G into dV. So net force will be integral dF, that is equal to integral rho G dV or rho G integral dV, or we can write it as rho V into G. So F is the upthrust force, which will be equal to the, this is the mass of the liquid and multiplied by G. So this is effectively the weight of displaced liquid by object. Let's take a problem. A wooden block floating in a bucket of water has 4 by 5 of its volume submerged. So as per the question, suppose this is the bucket of water in which wooden block is floating and its 4 by 5 volume is inside the water. So in this case, weight of block is balanced by the buoyant force. That is the force due to the weight of the displaced liquid. This implies that if mass of the block is m, so weight will be mg. This will be equal to the buoyant force, and buoyant force F is rho Vg. Density of the water is say rho W into volume which is inside the water. So it is 4 by 5V. It is a displaced liquid into G. So this is our equation number 1. When certain amount of an oil is poured into the bucket, it is found that block is just under the oil surface with half of its volume under the water and half in oil. The density of the oil relative to water is. So in this problem, now oil is poured into the bucket. So oil is above the water, and the block is such that half of its volume V by 2 is in oil. This is the oil, and half of volume is in water. So now weight of block is balanced by the buoyant force due to oil plus buoyant force due to water. Weight is mg, which we have already taken, and buoyant force is rho vg. For water, density is rho w into volume is v by 2 into g, plus for oil, density is suppose rho oil into, now volume of the displaced oil is v by 2 into g. On simplifying equation number 1 and 2, left hand side is mg. So comparing, we will have, comparing equation 1 and 2, we will have rho water into 4 by 5 into v into g, that will be equal to rho water into v by 2 into g plus rho oil into v by 2 into g. Here vg is common on left hand and right hand side, so we will have simply rho water into 4 by 5 is equal to rho water into v by 1 by 2 plus rho oil into 1 by 2. Taking the term to left hand side, we will have rho water into 4 by 5 minus 1 by 2. It will be equal to rho oil into 1 by 2. As we have to find the density of oil with respect to water, so this implies that density of oil by density of water, it will be equal to 4 by 5 minus 1 by 2 divided by 1 by 2, or it is equal to, this is 10, this is 8 minus 5 by 1 by 2, or it is equal to 2 into 3 by 10, or we can write it as 0.6. Hence option A is the correct option. Next question is, a jar is filled with two non-mixing liquids 1 and 2 having the densities rho 1 and rho 2 respectively. A solid ball made of material of densities rho 3 is dropped in the jar. It comes to the equilibrium in position as shown in the figure. Which of the following is true? We know that on mixing two or more materials of different densities, being the heavier, higher density material settle down, and the lighter density material will be on the top. Therefore, we can arrange these densities accordingly. Rho 1 is less than rho 3, less than rho 2. Hence option D is the correct option. Next question is, density of seawater is 1.03 gram per cc. A ship passes from the fresh water into seawater. It will rise, sink, remain at same depth, or rise or sink depending on its shape and size. We know that an object of weight mg floats onto the liquid if this weight is balanced by the buoyant force given by the rho vg, where rho is the density of the liquid, v is the volume of the liquid displaced by the body, and g is the acceleration due to gravity. So in our case, the ship passes from fresh water into seawater. So weight of the ship should be balanced by, if it is in fresh water, then we will write it is rho density of the fresh water into volume of the fresh water displaced by the ship into G, and it as passes to seawater, so this weight should also equal to density of seawater into volume of seawater displaced by the ship into G. Therefore, we can say that density of fresh water into volume of fresh water must equal to density of seawater and volume of the seawater displaced by the ship. Because density of sea is higher, it is 1.03 gram per cc, where density of water is 1.00 gram per cc at 4 degrees Celsius. So volume of the seawater is lesser. So we can say volume of seawater displaced by the ship is lesser than the volume of the fresh water. That means this implies that a smaller part of ship inside the seawater. Therefore, we can say it will rise. Option A is the correct option.